Yeah, thank you very much. I think we're missing a picture here. Nice. All right, so as you can see by the overlapping logo and the text, I won't win any design awards for this. But first of all, welcome everybody. I will give a talk about the evaluation and development of machine learning models, a quick introduction. And first, some things about me. I'm currently a graduate student at KIT here in Karlsruhe. I used mainly the pytorch framework for machine learning models. I have more than 4 years experience with it. So I've worked with, I think, more than 20 models in various domains, including video prediction, time series forecasting, image classification, generative image modeling, natural language processing, and a few more. So, safe to say I've got some experience. And I will soon, probably, if all goes as planned, end of year, I will start my doctoral program. So I will stay in the field. Now, why did I get into this field? Well, when I was a young child, I watched Star Trek: The Next Generation. Around 6 or 7 years old, I started, I believe. And Lieutenant Commander Data is an artificial life form who was very similar to me, at least I could identify with him, because he had difficulty understanding this illogical world, where things do not always go as you think they will. And he had this childlike innocence, and he had to learn, essentially, everything around him. And I thought that was really cool. And so I began reading books from Isaac Asimov, where he describes very developed societies, which, to a degree, of course, developed through the introduction of machine learning and general artificial intelligence, which fascinated me, those future worlds, and also the problems that came with them. Now, as soon as I got into the field in university, it felt kind of like cowboy maths. So in the imagination of a child, the Wild West is something where you can go anywhere and discover new things just by choosing a direction and going straight for it. And math and machine learning feels very similar because it hasn't been fully explored yet. There are so many directions you can go, and you can still find new things. You can contribute to a field. You can make discoveries that nobody else has done before, which are meaningful. I want there to be a more independent research, not just one from institutions, be they private or state-funded. And lastly, machine learning to me is a lot of fun. You can be really creative, and this is something that you cannot do in lots of other research fields, at least as I understood it when I talked about research, when I talked about it with researchers of those fields. So, when you begin, you first have to gain a basic understanding of the field. And while there are online resources which you should use to gain basic understanding of concepts, most papers in this field that are used are completely free. So they're an archive or you have other means, and everybody can access them and read them. And through the reading of those papers, you gain scientific understanding, and even if you don't understand them at the start, you understand them better and better and better, and you garner real understanding of them. With those online resources, most of them are shallow, or they're for people who have a vague interest but are not that invested in actually developing new models. So each new paper that you've read and understood, and by understood I don't mean you can vaguely say what it does, but I mean that you could stand up, give a 15-minute presentation to someone who vaguely knows the field, and they get what the concept of this paper is. When you understand papers in this way, your mind can work with them. You can work off of the ideas that these papers present, and this means that you essentially can make new connections. You suddenly get a flow of ideas whenever you read something, because your own head makes connections to other papers. highlights differences. You see, you begin to automatically ask yourself questions, why did they do it this way here and why not there? And could you perhaps apply this to that? And well, this is exactly what leads to research. Now, when you read those papers, I would also urge you to look at the repositories connected with them, because oftentimes when authors release those repositories, the code quality is pretty good. And you can also collect the data sets from them, which you will need if you want to evaluate models. Because there exist many data sets out there, but what differs are, for example, the pre-processing. So while a data set may be accessible to everyone, people may pre-process it differently, and there may be a research standard. And those research repositories often will adhere to that standard. So you're doing it the right way if you use their code, or at least look at their code and work off of it. Now, next thing, not all papers are equal. When you look at them, I would recommend you check the authors first. So there's H-index and I-index, essentially measurements, crude measurements, for knowing how popular a paper is or how good quality a paper is. You can also look at papers from peer-reviewed conferences, and I would also urge you to read those papers meticulously, not just skim them, because only then are you reading new keywords, which you can later on use for search. Because as soon as you want to search for something specific, you will need the right keywords, or there's a very, very slim chance that you will actually find what you're looking for, even if it exists. Now, when you read papers, you will notice with some keywords that the meanings are very similar. For example, hypernetworks and dynamic neural networks. Dynamic neural networks can change their structure or weights during runtime based on their inputs, whereas hypernetworks are networks that output weights for a different network. You can see the similarity, and authors will not use those two terms interchangeably, but they draw the line between those two terms differently. So whereas one author may draw the line a meter to the left, the other author will draw the line a meter to the right. And some of the challenges that hypernetworks and dynamic neural networks face are similar. And only if you read the papers can you really assess that. Now, I have not tried a lot with LLMs, but in my experience, LLMs do not draw these kinds of connections. Those things are information that you need to work out on your own. Now, if you want to start evaluating a model, what's the minimum that you will need? Well, you need a data set to actually run the model. Then you need a model and the baseline. You need a baseline because otherwise you're running your model in a vacuum. You don't know how it compares. And you could think that the performance on the data set is really good, but it actually isn't. And the baseline should also be in your own framework because otherwise it may also not be comparable. If you haven't checked that your framework adheres to the exact same standards that the other models that you use as external baselines have. Next, then, you of course need the optimizer to tune your weights, to essentially allow your model to perform better on the task that it does. And lastly, you need evaluation and recording. Now, in evaluation, you need to decide what metrics you use. So there are cases where you do not use the same metric that you use for training for the evaluation of the model. And lastly, recording is very important because otherwise you might make an experiment or conduct an experiment and interpret the results in a certain way, for example, negative, and then 3 days later you don't have the results anymore. And the results included some interesting finding, like, for example, a difference in the loss curve or something. Next, the barrier to coding for machine learning models isn't really that high. Python is a very, very basic language, is a scripting language, a very low level. Not low level in the same case as C is, but it is very easy to understand. Next up, the PyTorch framework I find also to be very organic in its use. The documentation is pretty good, though some of the functions are ambiguous in the way that they work. So what I would recommend there is to just write a short script that doesn't take that long and make sure that you understand the operators correctly, because sometimes having a little difference in the math makes all the difference in the performance. And lastly, I would also urge you to test the performance when you're optimizing the model for speed, because while some operators seem interchangeable, depending on the context that you're using them in, they have very different runtimes or very different memory footprints. So test that yourself. And I used free LLM just to try it to do some math-heavy work, so higher dimensional tensor computation with an Einstein sum, but at least the free ones didn't produce good code, so I wouldn't recommend them. If you do the math-heavy implementation, just do it yourself. Do it on paper first, then do it by machine. Now, if you have a project and you know what you want to do, and you search online for a repo, there's a good chance that you will find a repo that does something pretty similar to what you're doing. Do not fall for these repos. A lot of them, though they might look popular or good, hide errors, do not adhere to research standards, or have some other issues. So what I mean by don't adhere to research standards is, for example, in generative image modeling, one of the metrics that you use is FID, Fréchet inception distance. And it has been shown that the implementation, so that the FID score is sensitive to, numerically sensitive to its implementation. So there is one implementation that most of the people in research use, and which is accepted as the de facto standard. And if you do not use this, and I have come across repos that do generative image modeling that do not use this implementation, then your values may be different and may not be comparable, which is something to look out for. So to not run into these issues, if you can, just use repos from papers. And lastly, it's not a difficult domain. Make your own repo. A lot of it is boilerplate code, and the rest isn't that much compared to other projects you could do. Now, of course, you should test. However, you also want fast development, and if you test everything meticulously, you won't have fast development. So static tests make sense when you test things like, is my data set correct? Do I have the correct splits? Things that always stay the same. But if you have a model implementation that changes 20, 30 times over the course of the project, it does not make sense to have a static test for that. So instead, I would recommend you to write a lightweight Python script, 20, 30 lines, and just run that to check the math, leave the boilerplate code as is. That will work if you took it from somewhere where it worked. And save the script, because you can do two things now. You can give it to other people if they want to check your work and just tell them, look, here is my verification script. You can verify that what I have come up with actually works. And it also mathematically works. Second, your function will probably stay somewhat the same, so when you save it, you actually have something to work off of and do not need to remake it every time. But this lightweight script also means that you have a very low barrier to testing, so I would urge you to really check every new mathematical thing that you program. Lastly, probably some people will shoot me mean looks, but this is research, not production. If your code works, but it is not very extensible, you can rewrite it. Code quality isn't the #1 priority here. The #1 priority is iterating through models and testing your ideas. And as long as that works, you're good. Now, you could get the idea if you develop a new method that it would be nice to compare the computational complexity of it. There are flop counters, so floating point operation counters in Python, which measure the floating point operations for example, only the backward pass or the backward pass and the forward pass. However, I have found these, I've tested I think 6 or 7 of them. I found these to not really work because they all have different sets of operations that they take into account, and I haven't found one that took into account all of the operations of my last project. So what I mean by that is there are modules like, for example, torch and linear, which is a simple linear layer, and some of the optimizers take that into account but do not take into account its functional version, which essentially does the same, just it takes a weight and is not an object. So essentially what I'm telling you is they all give different answers and none of them are correct if you do something else than the standard. So you have 2 ways to get around that. One is to take a pen and take a paper, make some assumptions, and get the theoretical flops, which researchers like. However, that does not tell the full story, so the other 2 methods are the easier one, which is just also give the runtime and things like memory utilization. And the other thing is that you can also use external flop counters. So on a system level, tell your system to measure how many operations are done or performed on the GPU. Then, of course, you can probably not tell any longer which part of the model contributed. But you have a flop number. So that's your trade-off. Now, what also plays into it is your implementation, of course, because different implementations use different amounts of flops. That is not the full story because, well, you could have a very low flop count sequential model, which is a lot slower on parallel hardware of today than highly parallelized code, which may take 10 times the flops, but only 1/10 of the time. So flops do not tell the whole story. And you, of course, have the option to optimize your kernel by having a custom-written kernel, which you can do. There are languages that do that. However, that is its own thing, and that is out of the scope of this presentation. Now, if you have ever coded, you will probably at some time have committed the sin of premature optimization. This is not only bad because of the modifiability, in our case of machine learning, but also when you have an implementation that is optimized, it often is not as easy to play around with anymore. And one thing that drives research is your ability to easily change a few lines of code and just try what happens. And so I think that you should make your code as naive as necessary so you can easily modify it. And again, keep in mind, this is research, not production. Not everything has to be perfect. Then again, the domain is very simple. So if you're before the decision of recreating or modifying your framework and both have similar-ish time scopes, just rewrite it. You will have gained experience since the last time you did. Your code quality will be better. Your new framework will be more extensible. And oftentimes, you're very happy once you did it. All right. If you do not want one of these giant tables, I would recommend you to automatically save the results somewhere. One way you could do that is weights and biases. I am not paid by them. However, I have used their service for years and found it to be satisfactory for my needs. You may come up with some other solution. But when you save your results, what should go in there? Well, first of all, you want your model configuration. So you want to know what you actually tested. You want your data configuration, all of that, your whole training configuration. Then changes in code always should lead to changes in recording. So you should somehow indicate which version of the code you're using, what you currently changed, because otherwise, in 3 months, you will see the same configuration run twice with different code, with very different results, and then you will be very unhappy. So I would recommend you always have some kind of system in place which automatically does this, or add a new hyperparameter. It can be as crude as you want it to be. The main thing is that you know what it means and that you have some kind of documentation. Right. Then metrics. If you have experiments and you want to do something new, sometimes the metrics that you use or the metrics that are common are not enough. If you improve the model in some way that is not yet captured by metrics, but is meaningful to the task, do not hesitate to come up with your own metric or search for a metric that may not be used as often, but still may make sense in your case. When you record data, and for example use weights and biases or some other method of data aggregation, you can and you will see patterns, and those patterns will enhance your knowledge. For example, here you see accuracy versus W, which is in this case width, and you can see that a slight pattern emerges here. It's not as clear yet, because there are other hyperparameters also being changed in this scenario. But if you got new knowledge, then that will lead to you rethinking your hypotheses with this new data point. And this will mean that you have then ideas for your ideas, because suddenly you know something more about the general thing that you're working on. So you have a better flow if you actually summarize your results and try to look at them in different angles, because that way you can have inference that you didn't anticipate you could have. So you should look at your results both in a qualitative and a quantitative way. Because if you just look at the numbers, you probably won't see this. And the last thing is for experiments is that you will at some point realize that some things that the model does, or something that the model does better or worse, there's a chance that you don't capture that with your current experiment. And that will lead to you designing a new experiment. And so you should make a culture, or a habit rather, out of analyzing your experiment and thinking about what ways certain things could invalidate your experiment. Because sometimes you see that your experiment has a slight gap which you can close with a really easy different experiment, and then that experiment can have an interesting or rather interesting results, which then again leads to new ideas, new hypotheses, and to more research. Now, every time you have an idea, write them down. You will forget them if you have a lot of ideas. What you see here is a graph of Obsidian, which is again, I'm not paid by anybody, but which is a program where you can organize markdown files in a graph structure, so you can explore the local graph, you can explore the global graph, you can essentially organize your ideas, and through these connections you can have new inference about your ideas. So you could see that two ideas are connected through a third node, and then if you have some new idea for an idea that already exists, and it's indirectly connected, you could also then think about, well, this thing I just thought about, is that maybe applicable to that as well? Is that something more general? So connecting them makes a lot of sense in my mind. Then if you have a lot of ideas like me, focus on a few ideas, let's say 5. Keep them active, think over them again and again, but really just focus on a single idea in your implementation. Because if you're approaching 20 ideas at once, then it will be a very long time until you have results. If you do one idea, then at some point you have results, and at that point you have new knowledge with which you can work and which furthers your research onto those other ideas. So working on them iteratively, while hard, if you have a lot of them and think a lot of them are good, does make sense. Right? And both positive and negative results are important because you can update your hypotheses, you can think about why you were wrong, what caused this, and even if you have negative results, it is still interesting and you can still work off of that if you analyze them properly, like I told you in the last slide. Now, I now want to come to some open challenges, one of which is expressivity. So what you see here is that on the left side here, you have a target distribution. The x and y coordinates are independently sampled from standard Gaussian distributions. That's why you see this yellow border here, because that's not really where a lot of the distribution density is. And what these models do is they try to approximate this distribution here. All of these models are very, very small. You can run all of these models on a CPU. You do not need big hardware. You do not need a GPU even. You can just do it on any old CPU. And so these models are, I think, of sizes, hidden sizes 200 or less. And the input size is 2, the output size is 1, I mean, which is pretty much clear from this experiment, because you have 1 output color and 2 output, or rather 2 input coordinates. And you can see here that these different blocks, they have very interesting patterns. And this kind of research, so checking whether, so all of these blocks are without bias and single layer feed-forward neural network architectures. And this experiment, again, you can do at home. This is still very interesting because it shows the limitations of these architectures, because feed-forward neural network blocks like this are used, for example, in modern transformer models between the attention blocks. So these have a broad impact, and they're not just used there. A lot of modern models fundamentally rely on feed-forward blocks. Right. Now, a second problem you could approach is state tracking. So recently it has been shown that some classes of recurrent neural networks can actually not solve state tracking, which is pretty much a very simple problem, where you essentially just have, as an example here, for example, a man standing in a field, and you have a very long row of directions that the man goes into. Then you add a bunch of noise between those directions, and then you see that even bigger models are unable to solve this task of knowing where the person is after all of these actions have been executed. A paper I would recommend here is The Illusion of State and State Space Models. A very interesting paper, especially if you're new to the field. Right, and this is something that isn't that difficult, because very, very easy models can solve this. So you could feasibly test on this problem on your CPU and try to modify existing models that have some advantages over the classes of models which can solve this problem to try and combine the strength of both kinds of models. Which, of course, would be fundamentally important for the whole field of machine learning. Now, another problem is the context window length in time series prediction. So what you see here is on the x-axis time, and on the y-axis some kind of signal. And your task in time series prediction is that you have some kind of known signal for the context window, and then your task is to predict it for the prediction window. Sounds easy enough. However, it has been shown that for a lot of models, increasing the context window size only improves model performance to a degree, and after that, it can even degrade it. And now, why is that? Why can't the model learn the same amount of information when it has more information, and the information it needs to learn is included in that? So you would expect that the model would be able to do that, but it isn't. And this, again, is something you can do on your own CPU. So data sets for time series forecasting often are a few megabytes or less. So you can just feasibly run that. You could even use your phone if you really wanted to. Now, another problem, or rather open question, are activation functions. We have a lot of activation functions, a lot of different activation functions. Some of them are outdated completely. Some of them are only relevant in certain fields. Recently, we have had Kolmogorov-Arnold networks, which introduced spline activation functions, which are also really interesting. But essentially, the question is, what kind of nonlinear function do networks benefit from the most? As their activation. And you can test that on any data set. You can use small synthetic data sets just to go through nonlinear activation functions, and you can just come up with your own. Right? Nobody's stopping you. You can just try whatever you think up, and maybe it's good. Maybe it's the next big thing. Who knows? Now, there are, of course, many more open challenges. Many are undiscovered. Many will remain undiscovered for some time. You can find your own problem, I'm sure. And finally, my thought about machine learning was always this. When you look at the big breakthroughs in machine learning, then mostly you can write those in 5 lines of code or less. You're 5 lines of code away from making a machine learning breakthrough in a field that is so important. If that's not motivation, I don't know what is. Right. Now, after this talk, I want to talk to you. I organized a self-organized session outside on the lawn. So we will meet at the edge of the lawn because there's something else going on the lawn. And I want to talk about machine learning and chaos, because I am not aware yet of any groups that do machine learning within chaos. I would like to build knowledge and skill independently of institutions, because I have some friends who also want to do machine learning, but who perceive institutions as a hurdle, because they don't have the connections to them, because there does not yet exist a research trend, at least not that I'm aware of, where people research completely independently of any institutions. Institutions meaning private as well as state-funded. So I want to talk a bit about that. Help me develop this idea. Help me listen to your feedback. If you have any other questions that will not be answered in this unexpectedly long time we have now for answering questions and open challenges, you can also find me there. Yes, then thank you for your time. And now we will proceed to the discussion part. So if you have some open challenges that you think aren't highlighted enough in modern machine learning research, please let me know. Otherwise, after that, we will come to questions. Thank you.
Okay. Anne, thanks for sharing these insights and your experience, and thanks for this great talk. I assume here a lot of questions. Mimi will walk around and get your questions. Is there any questions?
First, open challenges.
Okay, then open challenges.
Nobody has a problem? That's great in this time. I think back there.
First of all, thank you very much for your presentation. It was very interesting. I have a question. You talked a lot about publications, about research, but I think most of us work for a company and also deploy models in production. What would you recommend for people doing that?
What is your goal? What do you want to do?
Actually applying machine learning, AI, deep learning in production, actually using those models and using not the old models anymore.
I think a good starting point is to essentially read the newest papers in that area, so you can There will be papers that are spotlights, mostly. You also get people talking about some papers a lot. You should read them. Some of them may make sense. Generally, I'm not that familiar with actual production machine learning because, well, I'm in research. So I think that's a field I cannot say a lot to.
Okay, but thanks a lot. Yeah.
Here in front.
Okay, I have 2 questions.
Yes.
First of all, how do you form the right baseline? And you were talking about data earlier and choosing the right data set.
Yes.
I wanted to ask, how do you form your comparison baseline at the very core? So I'm assuming, the way I understood it, that you want to go off of other models' results as well?
Yes.
But somewhere those results also have to have been compared to a baseline.
Mm-hmm.
So my question is, where do you start to form this? Where do you, or how rather?
Usually, if you have papers from peer-reviewed conferences, they will have some state-of-the-art comparison. And usually the models in there are kept for a bit of time, let's say a few years. So if you take results from such a paper, then you will have multiple baselines in there which can verify your results. You don't need to have every baseline. It is, I think, impossible to have every baseline, even every baseline that came out in the last 2 years, because machine learning is a rapidly developing field, and you just cannot keep up with everything.
Okay, so what you're saying is you should rely on peer-reviewed papers for that?
Yes.
Okay. My other question was about the context window size.
Yes.
You said the bigger the context window, the more challenges a model will have, or the more problems it will have.
Yes.
Just an understanding question, the context window, if you are increasing it, are you adding irrelevant data and you're expecting the model to extract the relevant data out of it? Or are you just providing more relevant data?
Both.
Okay, so it struggles either or.
Because, I mean, if you have very little data, then most of the data will be, quote-unquote, interesting to the model. If you add years before that point, there will be a lot of redundant data and a lot of noise in that data. But theoretically, it could also allow the model to capture new long-term dependencies or see some rare events that you previously couldn't have. So yeah, it's a mixture of both.
Okay. Can I add a question to that?
Yes.
What would you say is the most relevant value that falsifies this data? Like, what is the most? You for example, you said noise.
Yeah.
What has the most impact on falsifying this data?
I mean, that depends on the domain, right? If you have a weather forecasting data set and the wind blows in the wrong direction and you have a giant data center pumping out heat around the corner where the wind comes from, that might affect your data. Okay. Even though, well, it shouldn't be there, but it really is there. The measurements aren't wrong per se, but these kinds of things can also be a shock in the data.
Cool. That was it.
Okay, here's another hand raise in the 4th row on the right side.
I think this person.
Hi. Hi. Thank you so much, first of all, for the presentation. You mentioned the problem of the model not being able to know where it's positioned after it moves. And we can see this problem very like clear when, for example, seeing the models play chess. Where,
yes. Yes.
And I was wondering, why is it such a big problem? Because I think all the models were only able to fix this problem like maybe 6 months ago, and it was such a huge problem. Like, why?
I think the paper mentioned here is from 2024, and it does propose a model that solves this.
Oh, okay, yeah. So it's not very
the way they solve it is not the way that most large models work today. And so essentially the solution they propose has some drawbacks which outweigh the benefits currently. And the reasoning they use in their paper as to why this is the case is essentially that you can approximate the classes of models which cannot solve this problem in linear time, I believe, or linear depth, or something along those lines. You should read the paper. I don't have it memorized perfectly. Please read the paper. Yeah. Do not trust what I just said.
Yeah.
Read the paper.
Surely. But thank you so much.
Essentially, you can. It's a different class of computation. So you know P and NP. So polynomial and non-polynomial time problems.
No, to be honest. But okay. I probably have to look it up.
So essentially, they have some argumentation around this kind of complexity evaluation, and they show that you can simulate other models in a way which means that you cannot solve a problem if it has infinite length.
Yeah. Oh, okay.
All right.
Thank you so much.
On the left side, I think the third row, and then in the 7th row.
Okay, thank you. When you have a problem and you want to solve it, how do you come up with an architecture for a model? So what's your approach there?
I read a lot of papers and I get a lot of ideas.
Okay, so...
read more papers.
Read more papers, okay, thank you.
And also play around
with the blue shirt. Yes.
So if you write it down with a pen and a paper and you can formulate your problem that way, just play around a bit and see what mathematical differences there are, how you can view certain things, and then think about how you can maybe view them differently or what you could do differently but achieve a similar thing. All right.
So how do you decide on the activation function? Would your approach be just play around with PyTorch, use all of them, and then look which gives you the best results?
So there are essentially these standard activation functions, so you can look at existing research, and for certain domains there are certain activation functions, or there's a set of activation functions which you could try, which is the current approach. I think it's not optimal yet.
So you decide depending on the domain of the data?
And the model, because both the model and the domain have a huge impact on the performance or at least are sensitive to the activation function. I think back there is somebody.
Last row on the right side.
My question is, how do you solve the compute problem? So if you want to work on a certain problem that requires a lot of computation for training or also for evaluation, and when you're working privately on it, it becomes really fast, very difficult.
Yeah, so there are data sets which you can use. There are also synthetic data sets, for example, for natural language processing. One resource that you can use, I won't name the servers, but there are methods to get free GPUs from a company, which I don't know if they read your data, but we're in chaos here, so we should assume that they read your data. So you can go that route, or you have to go smaller if you don't want to invest a lot of money.
Is there a scientific way to somehow approach a large problem and make it smaller to for the models somehow?
That's outside of my expertise, but I think there is a synthetic natural language processing benchmark, and you could look at what they did. Maybe that could give you some insight. Otherwise, you could try to approximate different functions that are used in it, or maybe you could try to reduce the problem to a lower dimension. I would look at research for that.
Thank you very much.
Okay, anybody else?
Yes, there's another hand raise in the 8th row on the left side.
So when you try to work with a model and you have new data, which I, for example, work with industry data, so it's new data, and I try to use models that have existed before, and the results turn out trash, and I test the next parameters and how to find parameters that work before even optimizing. So I just like do a few runs with something that's similar to the paper, but oftentimes that won't work on new data. Is there a method to approximate valid parameters, or how do you do that?
I have, essentially, with modern terminology, I have only worked with pre-training models, so I have not trained any existing models, or not knowledge distillation either, because, well, you could train a model which at the same time takes in the new data and has knowledge distillation from some other model going on, which could work, but then again, that could be a lot of compute, so it could be expensive. So yes, it's outside of my field of expertise.
Okay, thank you.
Okay, it seems no more questions. I have a question coming back to the activation functions. I'm not so deep in that subject, so is there a way to customize or optimize these functions?
Yes, so some of the functions have a single parameter that you can tune, and for example, the spline activations, at least as they are used by the Kolmogorov Aron networks, they have different grid points, which you can essentially tune the splines in. So have you ever looked at spline approximation?
Briefly.
Okay, then you have these parameters where you can set how much each spline is apart, right? And
guess so.
You can essentially do the same here, but you have multiple grid points where you have splines at each grid point. And you can essentially create your own activation function through that, and which can have pretty complex behavior.
Okay, thank you very much. So there are no more questions. Then again, please show some proper respect to Anne. Come on.
We got one more question.
Oh, right one more question. Sorry.
I mean, I'm still a machine learning noob, so could you please explain, like there was an interesting picture with like lots of colors, you know, like this one. Could you please just explain the differences? Like, explain what exactly.
Okay, so I have a mouse here, yes. Okay, so for example, so I have forgotten the order, to be honest, but these are vector distance, dot product, circle approximation, and the one on the last row is a combined function of multiple other functions. And you can see here that, for example, well, I need to see it from this angle, it's a bit difficult. For example, here you can see the bordering lines are very, very sharp, and gated linear unit without bias can only produce these kind of bent lines, which means that it cannot really approximate this problem well. Same with, for example, MLP and glue trying to approximate the circle. They can essentially only approximate this outer ring here, which is then this area. And the center, because of the missing bias term, architecturally cannot be captured, though we see that when we mix both of these architectures, they perform a lot better. Well, with Khan, you can very clearly see the splits, because the formulation of Kolmogorov-R network that was used for this experiment lacks a linear output projection, so these sharp edges here will remain. Well, MI is a multiplicative interaction layer, so essentially it uses a tensor weight, third-order tensor weight rather. And you can see that it is not able to solve, well, every problem but the first one. Now, this is an architecture that is not yet on the market. It will hopefully be very soon, but you can already see it is quite promising, so stay hyped.
Yeah, but can you give me an example of real-life things, like what is like a problem, for example?
Okay, for example, the first or second row is vector distance, and if you have in your data representation two vectors which you need to know the distance of, for example, you have a car and an object that the car should not hit, then it would be very beneficial to the network if it could know how far away it is from that object. And this could, with some of these, be calculated within a single layer.
Okay, thank you.
All right, then please do not forget, anyone who is interested is bound to come to this meetup. I see you back there. You had a question, I believe. Then the mic shall be brought to you.
So I have a question, and that is, how would it need to be expanded with machine learning to solve AGI? Because I had that question for a long time, and I just can't wrap my head around it, and yeah.
Well, if I could answer that question, I would not be here, I believe. So essentially, we don't have the perfect solution to AGI yet, of course. There are a lot of ways we have not gone yet, also because of the computational complexity, computational load. If we could analyze the brain perfectly and perfectly mirror everything that it does, then we would have an intelligence as general as humans. So technically, I deem it possible. When that will happen, I cannot tell you. A lot of predictions of this kind have been made in the past, and yet, as of yet, none of them have held true.
Okay. Thank you.
Okay, is there any way how I can reach out to you if I'm interested on more details?
You can join the chat room, for example, for GPN. My matrix name there is Lithium 0. So you could do that.
Okay. Then, again, show some love.